Here is another attempt to inject a structure into the Learn dictionary, and this time we will target unitary matrices. I remind you, unitary matrices are square and have orthonormal columns. Broadly speaking, these can be considered as rotation operators in high dimensions. Also, their inverse is given simply by the transpose of the matrix. Why would we want the dictionary D to be unitary? Well, here is the general dictionary learning task, and if we require D to be of this form, then pursuit becomes very easy, as the thresholding algorithm becomes ideal in this case. Another benefit has to do with the number of degrees of freedom. A square and unitary matrix of size n by n is fully defined by half of n squared numbers. This means again that we could train on fewer examples and expect a generally better behavior. So let's design the training algorithm. As usual, it will have the structure we have already seen of initialization, followed by iterations in which we update the representations and the dictionary. When initializing, we must choose a unitary D. In the pursuit stage, we use the thresholding algorithm. And when we are to update D, this is the problem we face. Find the unitary D that minimizes the least squares expression. How should we solve this? The problem we have just defined is known as the Procrustes Analysis. Procrustes was a strange character in the Greek mythology due to his habit to cut people's leg to fit them to a given bed. Please read more about him in Wikipedia. Anyway, in our story, D operates on the columns of A, rotating them. We are seeking the rotation operator that will bring to a best fit between the rotated columns of A and the columns in Y. So, just like Procrustes, we are torturing A by rotating it. Surprisingly, this seemingly tough problem has a closed-form solution, which we present next. Here is the expression we aim to minimize, and we simply opened it into its three ingredients. Have you noticed that all our expressions use the trace operator? This stands for the sum of the diagonal elements in a matrix. I will leave it to you to find out why we use it here. Observe that the third term has the appearance of D transposed times D, which is by definition the identity matrix, and thus it vanishes. Therefore, this is our maximization goal, and it is equivalent to this minimization task. An appealing property of the trace operator is the fact that the trace of AB and BA are the same, as long as the two multiplications are well defined. Thus, we allow ourselves to move Y transpose to the right. The next step is to observe that A times Y transposed is a known matrix. So let's just assume that we have computed it and replaced it by its singular value decomposition, SVD. In this decomposition, which always exists, U and V are unitary matrices, and sigma is a diagonal matrix with non-negative entries. We are nearly done. This is the expression we aim to maximize, and now we make use again of the trace property in order to move V transpose from the right to the left. Observe that V transpose times D times U is a unitary operator since all three are unitary. So let's just call this Q. The unitary matrix Q multiplies the diagonal matrix sigma, and the maximum is obtained by concentrating all the energy of Q on the main diagonal. Observe that here we exploited our knowledge that the singular values are never negative. Thus, the optimal Q is the identity matrix, and this implies that the optimal D is V times U transposed. That's it. This is the closed-form solution to our Procrustes analysis. Back to our dictionary learning story. When time comes to update D, we compute A times Y transpose and apply an SVD on it, and then we get the update of D by setting it to be V times U transpose. An interesting twist over the above is when we target a dictionary that will be a union of several unitary matrices. Suppose, for example, that we want our D to be built of D1 and D2 merged into an n by 2n matrix. The problem presented here defines this learning goal in which D1 and D2 are unknowns along with the representations multiplying them. Why would we be interested in such dictionaries? Well, a vivid discussion on such combinations appeared in the signal processing literature, motivated by both theoretical aspects and practical ones, but we will not dive into these stories here. Our interest will be in the training problem we have just defined, as explored by Gribonval and his students. The above-mentioned paper proposed a most natural way to train D1 and D2, in which we freeze one and train the second and iterate this way. More specifically, when we freeze D1 and A1 and aim to update D2 and A2, we obtain the problem we have just studied, so we can invoke the algorithm presented. Then we freeze A2 and D2 and update A1 and D1 in the same fashion. Both blocks are easy to handle. In fact, we could apply only few iterations in each of these blocks and even mix the update steps of the 4 ingredients in various different orders and still get a sensible algorithm.